Hello guys, it's your host Elias with you again. Today we will be presenting Discrete Structures homework number 6. We were given 4 different sections in chapter 6, so we will do section 6.1, questions 8 and 9, section 6.2, 3 and 4, section 6.3, 8 and 9, and section 6.6, 5 and 6. So we'll hop right in. I'll go ahead and show us our questions and then I'll explain my answers. So we hop right on over to our first section, 6.1, questions 8 and 9. Let me make this a little bit bigger so you guys are able to see the whole page. Perfect. So we got 8 and 9. So question 8 right here. How many different 3-letter initials with none of the letters repeated can people have? That is question 8. Question 9 says, how many different 3-letter initials are there that begin with an A? Alrighty, so we'll hop right in. I'll show you guys my journal and I'll show you guys how I got to my answers. So first question, as we can see here, section 6.1, question 8. So by the product rule, we can, and I'll kind of explain how I understood it and go on from there. So we're looking for a 3-letter initial, or a 3, let's see what it says. Yeah, 3-letter initials, right? So 3-letter initials, we will have 3 letters. So the first letter will be chosen out of 26 letters, because that's how many letters are in the alphabet. And we cannot repeat our initials. So we have 26 letters we can choose from for the first, 25 for the second, and 24 for the third, meaning that each time we take a letter out, the letter we chose, right? So how many different combinations can we have of the 3-letter initials? Well, simply by the product rule, if we multiply each of these together, we get a total of 15,600 combinations. So that's how we got to that answer. Now comes the second part. So the second part, or the second question in this section 6.1, is how many 3-letter initials can we have that begin with the letter A, right? So the first initial, we can only have 1 letter, which is A. So second initial, we choose from 26 letters, and third initial, we can choose from 26 again, because it did not say that it did not have, or it could not repeat. So there we have it by the product rule again. If we multiply these, 1 times 26 times 26, we get a total of 676, which you see here. We don't quite believe me, I'll do a quick calculation to show you. So pull out the handy dandy calculator. Hope you guys can see that. So 1 times 26 times 26 equals 676. So as we can see, that is correct. Alrighty. Let's move on to the second section, which is section 6.2, as we see here. So let's hop on over to our book once again. Section 6.2 is on page 426, so I'll hop right over there. 426. And we have here questions 3 and 4. So questions 3 and 4. Question 3 states, a drawer contains a dozen brown socks and a dozen black socks, all unmatched. A man takes a sock out at random in the dark. How many socks must he take out to be sure that he has at least 2 socks of the same color? B. How many socks must he take out to be sure that he has at least 2 black socks? Alright. Question 4. A bowl contains 10 red balls and 10 blue balls. A woman selects balls at random without looking at them. How many balls must she select to be sure of having at least 3 balls of the same color? B. How many balls must she select to be sure of having at least 3 blue balls? Alrighty, so 2 different questions asking, or pretty much worked about the same. So we'll go on to our journal and we'll go ahead and explain these. So question 3 first, about the socks, right? Or which I have right here. So we have read that for you. So we have a drawer that contains a dozen brown socks and a dozen black socks, right? So we have a dozen black and a dozen brown. So the first question that was asked, which was 3A, states that how many socks must be taken out to be sure that he has at least 2 socks of the same color. Well, in these types of questions, we always take the worst case scenario, right? So the worst case scenario is that he pulls out one sock of one color, then another sock of a different color, and since there's only 2 different socks, a black and a brown, the third one must be one of each. So that way that we can come to this conclusion that he will have to pull out exactly 3 socks to have at least 2 of the same color. Now we go on to question B. How many socks must he take out to be sure that he has at least 2 black socks? Well, worst case scenario, again. So, there's 12 brown socks and 12 black socks, right? Worst case scenario is that he pulls out 12 brown socks before he pulls out any black socks. So, this leads us to believe that worst case scenario, he will have to pull out exactly 14 socks to get 2 black socks. This is because if he has his worst day ever and pulls out 12 brown socks, he will have to pull out 2 more socks in order to have 2 black socks. So we get 14 socks just based on the worst case scenario. So there you go. Question 3 is answered. We'll hop on to question number 4. And question 4 states, and I'll repeat again, a bowl contains 10 red balls and 10 blue balls. A woman selects balls at random without looking at them, right? So question 4 has a part A and a part B. So A says, how many balls must she select to be sure of having at least 3 balls of the same color? Again, worst case scenario, right? Or yeah, again, worst case scenario, right? So we get and we pull out a ball randomly, right? Let's say the first one is red, right? Then the second one is blue. So there you have a blue and a red. The third one is red. That makes 2 reds, 1 blue. But the fourth one is blue. So right now she's at an even. Red and blue, red and blue. So the fifth one will decide which of the blue or the red she pulls out. So if she pulls a 5th ball, no matter what, she will either have 3 reds or 3 blues. Which leads us to this conclusion that she must pull 5 balls out in order for her to have 3 of any color, or 3 of the same color. Next question, B. How many balls must she select to be sure of having at least 3 blue balls? Now it gets specific, not any color, but blue balls. So we have 10 red balls and 10 blue balls, and just like I said, worst case scenario, he has his worst day and has the worst luck and pulls out all 10 of the red balls. So in order to get 3 blue balls, she will have to pull 3 more out. So that leads us to this conclusion that she will have to pull it out exactly 13 balls in order to be sure that she at least pulls out 3 blue balls. And there you have it. Section 6.2 is finished. We'll hop on to our next section. So I'll go back in our book. Let's see. So here in our book, we jump over to section 6.3. That is on page 434 of our Discrete Structures book. So jumping right over. Here we are doing questions 8 and 9, so I'll look for those. Here they are. I'll read them briefly, and then we'll go into what I have, right? And how many different orders can 5 runners finish a race if no ties are allowed? Awesome. Next question. How many possibilities are there for the win, place, and show first, second, and third positions in a horse race with 12 horses and all orders of finish. And all orders of finish are possible. Awesome. So, we'll jump over to our journal. And we have here questions 8 and 9, right? Talking about permutations. And for permutations, we're going to use this corollary for combinations, which is P n comma r is equal to n of, I forgot what this is called, 1 second. Factorial, sorry. Totally lost the word, but I got it now. So, n factorial divided by n minus r factorial. Alright, so it explains it what each thing is. So P, number of ways to pick. N is number of things to pick from, and R is number of things to be picked. Alrighty, so we jump into 8. 8 said, and I'll hop right on over to our book. And how many different orders can 5 runners finish a race if no ties are allowed, right? So, we come right on over. So we have 5 runners, right? 5, and we can pick from 5. So, we use this corollary for combinations, which is 5 factorial divided by 5 minus 5 factorial. So, we do 5 factorial, which is let me look right over here, put our calculator to do factorials. It's just simply, we take 5 and times it by each previous number. So, well, not like I said, but I'll just show you. So 5 times 4 times 3 times 2 times 1, right? Gives us 120. So is equal to 120. And now we have to do 5 minus 5, which is equal to 0, and 0 factorial, which is equal to 1. So 120 divided by 1 gives us 120. So there are 120 ways to, as question 8 says, there's 120 ways to order the 5 runners to finish the race, where no ties are allowed. Question 9, I'll read it again so we can have it fresh on our memory. How many possibilities are there for win, place, and show first, second, and third positions in horse race with 12 horses if all orders of the finish are possible? So, hop right back over. We can only show first, second, and third, right? So, we use the same corollary for combinations, which is this right here. So, we have things we can pick from are 12, but we can only show 3, right? So 12 horses, 3 places. We insert that over here to our little function. So 12 factorial divided by 12 minus 3 factorial. Awesome. So get right to it. I pre-calculated this before recording, so 12 factorial is this number. This equal to this, and our answer is 1,320. So there are 1,320 to show for second and third from 12 horses. Alrighty, that completes our section 6.3, and we'll hop right on over to our last section, which is section 6.6. So, section 6.6 is on page 459. And we are doing questions 5 and 6, I believe. Yep, 5 and 6. So these are work the same. So I will not go ahead and explain each and one of every one of them. Sorry. So I'll explain 1 or 2 of 5 and 1 or 2 of 6, and then just show you guys the answers for the rest. So it says find the next larger permutation in lexicographic order after each of the permutations. Same thing for 6, but it gives us different numbers, right? So we'll hop right on over to our journal so I can explain. So we have question 5a, which the number given I put up here. And how we do this is we compare first the last number. So in this case, 1, 2, 3, 4. So the fourth number and the third number to see if the third number is greater or less than the last number. If it's less than, we stop here and then we order what's behind it in ascending order. If not, if 3 is greater than 2, we keep on going and compare 4 to 2, then 4 to 3, and we keep on going like that. So we have right here what I wrote. So compare the last two. 3 is greater than 2. We keep on going. Compare the second and fourth. 4 and 2. 4 is greater than 2. Compare the second and the third. So we keep going. So 3 and 2 are compared. 4 and 2. Then 4 and 3. Then I'll go 1 and 2. And since 1 is going to be less than 2, that's where we stop. We put 2 over here. And we line the numbers up in order from least to greatest, which we did here, which are these numbers 1, 4, and 3, which is kind of what we explained over here. So we compared second and third, then we compare first and fourth. Since 1 is less than 2, we select the first and fourth, we switch them, and then we order the rest and from least to greatest. So as you can see, B, we did the same thing. We have this number right here. We compare the last two, 2 and 3. So 2 is less than 3, so we can already stop there. So 3 switches over to this. Since there are no more numbers to organize, we just simply put 2 back here, and this will be our new number. So like I said, I'll only explain 2, and then we'll keep on going. I'll just show you guys my answer. So right here we're getting this number ordered. It would be like this. D, this is our initial number. This is our number we got. E, this is our initial number, and this is the number we came up with. This is our initial number. This is the number after we did the process. Quite a large, or quite a long process, but we got it. That completes question 5. Off to question 6. I'll go ahead and explain again. I didn't write out as much, but we are doing the same thing, comparing from back to forward. So our number given was 1,342, so we compare the last two. Is 4 greater than 2? Yes, it is, so we keep on going. 3 and 2. Is 3 greater than 2? Yes. So is 3 greater than 4? No. So we stop there, select 3 and 4. We switch 4 over, so it'd be 1,004, and then we ordered 2 and 3 since they were behind and in order from least to greatest. So 1,423, which is the number we got. Same thing with this number over here. I'll explain this one and then we'll just go on forward, just showing you guys the answer. So we have the number 45,321. So we compare the last two. Is 2 greater than 1? Yes, it is. Is 3 greater than 1? Yes, it is. Is 3 greater than 2? Yes, it is. Is 5 greater than 1? Yes, it is. Is 5 greater than 2? Yes, it is. Is 5 greater than 3? Yes, it is. So we go on to our last. Is 4 greater than 1? Yes. 4 greater than 2? Yes. 4 greater than 3? Yes. 4 greater than 5? No. So we select these two, switch 5 to the beginning, and then we order these numbers from least to greatest. So 1, 2, 3, and then 4, which we get this number right here, 51,234, which is our number. So from here on out, I'll just kind of give you guys my answers that I got. This is the number we started out with, 13,245. This is the number we now have, 13,254. Following the same process, going to the back, the number given was 612,345. The number we got now is 612,354. E, Number given was 1,623,547. The number we got was 1,623,574. Next number we have right here, 2358741 The number we got, 2358741 Not a lot of change because the first comparison that we did, this number was greater, with less than the last number. Same here and same here. So there wasn't a lot of change. And with that, guys, we have completed homework chapter 6 for discrete structures. Thank you guys so much for watching, and we'll see you in the next one. Thank you. Goodbye.